So, welcome back to this course on linear algebra. Now, today I am going to start a new topic called linear maps. So, as usual, K is our fixed scalar field. And what we want to do is, actually we want to study maps of vector spaces which preserve structure. So, structure preserving maps. Maps between K vector spaces. This is what we are going to study. So, recall that a structure of a K vector space on V consists of two things. One is the addition, such that with addition on V, which makes V plus as an abelian group. And the second one is scalar multiplication of K on V, which is a map from K cross V to V. These two together form a vector space structure on V. And if you have two vector spaces V and W, both are vector spaces over the same scalar field, and suppose you have a map F from V to W, map, then we say that F is a homomorphism of K vector spaces if it should preserve the addition and also it should preserve a scalar multiplication, or it should be compatible with this structure. That means first f of x plus y equal to fx plus fy for all vectors x and y in V. And remind you that whether you add the vectors in V first and then apply the map F, or apply the map first and then add the vectors in W. So, in principle these two operations are different, but it is clear from our writing where we are operating. Secondly, f of Ax should be equal to Afx, where for all scalars A and for all vectors x. If both these equations are satisfied for all scalars and all vectors, then we say that f is a homomorphism of vector spaces. If one want to put both together or together, only in one condition we can rewrite it as f of Ax plus By equal to Afx plus Bfy for all scalars A, B in K and for all vectors x, y in V. Then we call it f is a homomorphism of vector spaces, or we will also just say that f is a K linear map. And in this section we are going to study the set of all K linear maps from one vector space to the other vector space. and soon we will see some examples. So, first note that F will be a if F is linear, then F will be a group homomorphisms of the abelian groups. It's a group homomorphism. So, therefore, in particular, as you would have seen in the case of group homomorphisms, identity of this group, which is 0 vector, will be necessarily the 0 vector of the vector space W. So, this is must. Okay. Also, one thing to note is, if F is bijective, in addition, if F is bijective, if F is bijective and K linear, then inverse, F inverse is naturally bijective and K linear. This needs little checking. The K linearity of F prime needs little checking, but which I leave it to you. So, in this case we say that F is an isomorphism of K vector spaces, and sometimes write like this. We say that F is an isomorphism of K vector spaces, or just K isomorphism. Okay, so some couple of notations which we will keep using throughout the course. If V and W two K vector spaces, then home K V W, this is a set of all K linear maps from V into W, and note that this is a subset of W power V. Remember, W power V is a set of all maps from V to W, and this is among them we have chosen only the K linear maps, and that we are denoting by home K V W. Just to remember, they are K linear for this, and home is short form for the homomorphisms, and we are going to study this object more intimately. So, the first thing to note is we can add two linear maps. If F is a linear map from V to W, G is a linear map from V to W, then you can define a new linear map from which we will call F plus G from V to W. This is very natural. This is defined by F plus G evaluated at x is same as Fx plus Gx for all x in V. This is same thing as saying that, remember, on V power W power V is also vector space, because it is a power of this vector space, and this is a K vector space with component wise structure. With component wise addition and scalar multiplication. So, this means that this home KVW is actually a subgroup of this. So, with this home KVW, with this plus, which is inherited from this pointwise plus, is a subgroup of W power V. Second thing to note is I can also define for any given scalar and any map, k-linear map V to W. I also have a very natural definition of the scalar multiple of F. AF is again a map from V to W defined by AF evaluated at x is AFX for all x in V. So, together with these two observations, it shows that therefore home KVW is a K subspace of W power V. So, now some particular notation when I suppose special cases when W is also V, then home KV, the linear maps from V to V, this I am going to give a special name, it is end KV. These are also called the set of endomorphisms. Of V, K endomorphisms, or they are also called K linear operators on V. And one of the main objective of the course on linear algebra is the study of K linear operators on a vector space. So, this is a K subspace, this is a K subspace of V power V. It has a more structure. So, moreover, the composition circle is a binary operation on endomorphisms, the set of K endomorphisms of V. So, that means we can compose two endomorphisms and get another endomorphism. So, that means we have such a map. Namely F compose G, you send it to G compose F. So, this is a binary operation and it has nice properties, namely properties along with the addition of this vector space of K endomorphisms, that is a pointwise addition or component wise addition, and this new composition along with that it is a ring. Remember, we have to check several things here which I am not going to check. One, the distributive laws, which connect plus and composition, and now this composition may not be commutative. In fact, most often it is not commutative. So, we have to check really two distributive laws, left distributive law and a right distributive law, and also the existence of identity. So, identity map of V is clearly K linear and is the neutral element for the composition. So all this together it forms a ring. Moreover, it also is a K vector space. So the K vector space structure, that means the scalar multiplication and this composition, they are compatible with each other. So, and scalar multiplication on endomorphisms and composition are compatible. That means whether for any scalars AB and any operators, any two operators FG, first we take the composition of two operators and multiply by the scalar AB, or you multiply AF, F by scalar A and B by scalar B by endomorphism, and then compose them. These result is same. That is the compatibility of scalar multiplication of endomorphisms and the composition, whether you scalar multiply first and then compose or the other way, the result is same. So such a structure is very important, and generally such a thing is called an algebra. Therefore endomorphisms of K endomorphisms of a vector space V is a K algebra. So we are going to study this K algebra in this throughout this course more and more intimately, and that is the reason why the elements of these are K linear maps and this is a K algebra. That is why we call this subject as linear algebra. More general concept of K algebra is it's a ring, and also it has a scalar multiplication of a field such that the addition of the ring and multiplication and the scalar multiplication, they are all tied together with all these compatibility conditions. That is called a K algebra. But I will not go into more general now. Right now our aim is to study this K algebra more intimately. So recall that whenever we have a ring, then we have invertible elements with respect to the multiplication, and that remember we have denoted by the cross on the top. So NK A cross, this is the set of invertible K linear operators on V. They are precisely the K automorphisms of V. Invertible, therefore they are bijective and K linear, and just now I above commented that inverse is also K linear. So they are precisely the K automorphisms of V, and therefore this is also usually denoted by OT KV. Sometimes I will also denote this by GLK, GLKV. Important thing to note about it is GLKV is a group under composition. And we are going to study this group more intimately along with the endomorphisms. GL is a short form for the general linear. All right. So let us see in the case, so special case, if V is K power n, this vector space, then usually GLKV also denoted by GLNK. and it is called nth general linear group. Okay. Before I see the more concrete examples, I would like to record the following theorem whose proof is very easy. I will try to say it orally, but we will write the statement very precisely. So let f from V to W be a k-linear map. Of k vector spaces V and W. Part 1 is concerns about the subspaces of V and the images of the images of the subspaces of V. So, if V prime is a k subspace, then its image under F, then f of V prime is also a k subspace of W. In particular, image of F, image of the map F, which is by definition f of V, is a k subspace of W. Second part, the other way, if W prime is a subspace of W, is a k subspace of W, then the inverse image of W prime. This is by definition all the vectors x in V such that f of x belong to W prime is a k subspace of V. In particular, the inverse image of the 0 subspace, which is also called kernel of F, which is by definition all those vectors x in V such that f of x is 0 is a k subspace of V. This is very easy to verify. So I will not write the formal proof. Proof easy to verify. Note that how do you check somebody is a subspace? You have to check two things. It is an abelian subgroup. It's a subgroup of V plus, and also it is closed under scalar multiplication. So both these conditions are merely verification. So I will not do it. First of all, note that if f is k-linear, then for any number of scalars, finitely many a1 to an scalars and n vectors x1 to xn in V, we check by induction f of a1 x1 plus 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 an xn equal to a1 f of x1 plus 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 an f of xn. This is very simple checking by apply induction on n, do 2 at a time and so on. Or even more generally f of the linear sum I in I ai xi equal to summation ai f of xi, where ai is in the tuple ai, I tuple ai belongs to k power round bracket I. So, that means almost all ai's are 0. So, this sum makes sense, and even this sum makes sense, and xi I in I, we have an arbitrary family of vectors in V. This is merely the earlier statement. Okay. So, further, okay. Another special case which I want to note is W equal to K. Then home K, all linear K linear maps form a vector space V into K. This is also called V star. I will denote this by V star. This is the set of all K linear forms on the K vector space V. Usually the word form is used when the values are in a scalar field, or there the functionalities people will also use it K linear functionals. They are functions because the values are in a field. Okay. Okay. So, remember that also when we have already proved V as a vector, every vector space as a basis. So, suppose Vi I in I is a K basis of V, then we have defined coordinate functions Vi's stars. They are functions from V to K, and they are also K linear maps, K linear forms actually, because the values are in field. So, that means that is Vi star are actually elements of V star for every I, and Vi stars have additional property, namely for every vector x in V, Vi star of x is 0 for almost all I, and wherever it is non-zero, that is called the ith coordinate of V. So, ai defined by this Vi star x I in I are called ith coordinate of x is called, and there are at most finitely many coordinates non-zero. So, this means the following, this actually is nice, this means we have a vector space, this K round bracket I, and we have a natural map from V, namely the map is very simple, any tuple ai I in I in K power round bracket I goes to summation ai Vi. This makes sense because only finitely many ai's are non-zero, and the fact that this Vi is a vector Vi is a basis of V means this map is injective and also surjective. Generating system will mean this map is surjective, and a linear independence will mean this map is injective. So, this map is actually bijective, and it is very easy to check that this map is actually K linear map. That means this is isomorphism of K vector spaces. So, I am not going to check that this is a k-linear map, because it is really easy. One needs to write only one line, but I will leave it for you to check it is a linear map. So, that means we have proved that every vector space is isomorphic to k power round bracket I. This is very useful, but also coordination will depend on this chosen basis. So, when we change a basis, the coordinates will also change, and this will allow us to do more general things in a more simpler way. So, we will take a break and continue after the break.